Welcome to part one of our notes on energy. Again, these notes are designed to give you a brief introduction to energy. They're designed to give you the basics of what you missed if you were absent in class or if we're flipping these notes, which means I'm going to put you in charge of taking a note so we can do lots of other activities when everybody's in the classroom. These notes are just designed to give you a basic introduction. We'll cover a lot more about energy, what energy is, and how it's produced in class. When we talk about energy, we talk a lot about electricity. And this is one of the reasons why we're talking about this topic in class. It's fairly important. By 2030, the United States electricity needs will increase by 45%. Now, if you think about that, 45%, it's not going to necessarily double, but it's almost half of that. And when we look at that, that means we're going to have a lot more power plants. Or we're going to have other ways, alternative ways of producing electricity. So it's going to be a fairly important topic in your lifetime because there's going to be a lot of debate about where do we get all this extra electricity from that we need. When we think of energy, a lot of times we think of the Energizer Bunny. Remember, the Energizer Bunny just keeps going and going and going. It's like some of you. You guys are like the Energizer Bunny. Some of you just keep talking and talking and talking. Well, when we think of energy, you probably talk a lot because you got a lot of energy. What is energy? Energy is simply the ability to do work. And think about that. If you are at home and you've got a lot of energy and you're bouncing off the walls, you can do lots of different things. Yeah, you got a lot of energy. You can do a lot of work. But are there ever some days where you just feel like you don't have any energy, that you're just really weak, that you can't do a lot of work? Well, again, it relates to energy. Energy is the ability to do work. If you have a day like that where you just don't feel like getting out of bed, it's hard to do a lot of work because you don't have a lot of energy. When we talk about energy, a lot of times we think of electricity. And electricity is simply the flow of electrons. If we were to take a wire and if we were to cut it in half, and if we were to blow it up large enough so that we could see it, we could see those electrons jumping from atom to atom to atom. Now, this electricity, you can also get electricity out of a battery. So this electricity, a lot of times, will flow in wires. But there are no wires inside this battery. But batteries are simply an energy storage device made up of one or more electrolyte cells. There's chemicals in this battery, and these chemicals are designed to create a flow of electrons. So you actually hook the wires up to the batteries, and it will flow through whatever device you have, and it'll flow back into the other side of the battery. That's why you have to have the positive and negative side of a battery hooked up, because you have to complete that circuit in order for the electricity to flow. Now, where do we get this electricity? We get this electricity from a power plant. And a power plant is simply a facility where power, especially electricity, is generated. Now, you notice it says power. Some power plants are designed to produce steam. Say a lot of universities, if they have lots of buildings, they'll have a power plant that will produce steam, which is used to heat all the buildings. And those are also called power plants. They may not produce any electricity, but most power plants do produce electricity. Now, here's this really, really simplistic model of a power plant. Now, a lot of power plants, if you look down here, they're going to have a fuel source. A lot of power plants in Wisconsin use coal or natural gas. Some may burn wood. A few may burn garbage to produce electricity. And all of these that do burning burn their fuel, and that heat is then used to take water and turn that water into steam. And as that steam gets heated, or that water gets heated, it turns into steam, and steam expands. And pretty soon it's used, when there's enough pressure, to spin what we call a turbine. And that spinning motion, the turbine is connected to a shaft up here, and that shaft goes right into something called a generator. And it's inside this generator where that shaft is spinning around and around and around. And it's this motion that helps to create the electricity to power things such as a toaster. Now, sometimes we don't need a fuel source. Sometimes the wind will spin the turbine directly to create the electricity. Sometimes in the case of solar energy, we don't have any spinning motion going on. It's a different process that creates electricity for us. Now, if we were to take a look at nuclear power plants, Wisconsin does have nuclear power plants, and they're not necessarily burning a fuel source, but the heat energy comes from the splitting of the atoms, the splitting of, a lot of times, uranium. and it's this splitting motion. When that happens, small amounts of energy is being released. And because there's so many different processes, there's so many different uraniums atoms splitting at the same time, it ends up producing a lot of heat. And that heat does the same thing. What it's going to do is it's going to heat up the steam, and that steam is going to spin the turbine. So what's a simplistic way of looking at this? Well, here's a tea kettle. Have you ever seen this happening? If you ever, my grandma used to have one of these, and she would put the tea kettle on, and then no matter where we were in the house, we could tell when everything was ready because all of a sudden the steam would come spinning out of here, and a lot of times would make a high-pitched noise. And if I was to take a spinning wheel right here, and if I was to put that right up to the steam, it would actually spin it. So a power plant basically works like that. So here's what a turbine would look like if it was in a power plant. And a turbine is simply a device with blades that are turned by a force that, such as wind, water, or in a lot of cases, high pressure steam. So when we look at it, here is your generator right here, and we can see it. And in here, you have a turbine outlet, and here you have your turbine. So inside here, you got the steam coming in, and it's spinning the turbine. It's connected to that shaft, and that shaft goes all the way over here into the generator, and this motion in here creates electricity. So if you like math, think of it as being like a math problem. First of all, you're going to have magnets. Your magnets are going to be found inside the generator. If you have magnets, you have copper wire. Again, you're going to have copper wire inside the generator. And if you add motion to it, what do you get? You get electricity. So this might be an example of a generator. You are going to have the spinning motion. So here you have your turbine right here. And something's going to be causing it to spin. It might be steam, it could be wind, but you have this motion. And you have magnets. Magnets was also part of the equation. And you have a lot of copper wire. And this wire would be wrapped around here. Now this is just the basic design of what a generator might look like. Obviously you're going to have a lot more copper wire than this. And as this spins around, it's that mechanical energy along with the magnets. What it's going to do is going to get the electrons flowing along this path. So the electrons are going to be flowing out, and they're going to be flowing back in, so more can be flowing out. And this is what's going to create electricity. So a generator is a device that turns mechanical energy into electrical energy. The mechanical energy is sometimes provided by an engine or by a turbine. So you can actually get a gas-powered generator to produce electricity for you. Now a generator produces electricity. So for example, here if we had wind spinning a turbine, and we've seen these wind turbines around Wisconsin. There's a new one that just came into production over on Highway 33 near Cambria. And if you take Highway 12 down towards Madison, Epic Company is putting in I believe 6 turbines on your way down towards Madison. So here again, you have your copper wire, you'd have your magnets inside here. So what do you get? You get your motion, you've got your copper wire, I'll put Cu for copper, and then you have your magnets up here. And these three things end up producing electricity. Now when the electricity comes out of a power plant, one of the first things that must be done is power companies have to step it up. And the reason for that is when we transmit it long distances, it's much more efficient if we step it up to say 300,000 volts or more. And that's why there's substations. Substations can do a couple different things. One, they can help step electricity up, but a lot of times if they're in your neighborhood, they're designed to step the electricity back down so that you can use them in your house. And a transformer is a device which converts a generator's electricity to higher or lower voltages depending on where you are. If it's by the power plant, it'll beef it up and it'll step it up and it'll send it along the transmission lines. If these are near your house, and we tend not to see too many of these anymore that are actually attached to the poles, a lot of times these are going to be in your backyard and it'll look like a green box. And if you do have one of those in your backyard, just stay away from them. They can be dangerous if you're playing around them. And what a transformer does, again, it will take the electricity out of the power plant and it'll step it up, and it will send it out at 300,000, maybe 400,000 volts. And the reason it does that once more is because it's more efficient to send it along its way at a higher voltage. And what happens is the power company, for example, here in Baraboo, do we get our power from any one power plant? And the answer would be no. You might say, well, yeah, don't we get it from Portage? That's the closest large-scale power plant. Well, power companies actually put their power out into something called the grid. And we have the power plant over in Portage. We have hydroelectric power plants in Wisconsin Dells and over in Prairie du Sac. In all those places, we talked about the wind turbines over on Highway 33. All those places put electricity out onto the grid. So even if, say, Columbia Power Plant had to go offline because maybe a part broke and they had to shut down the plant, we could still get electricity here in Baraboo because we'll just draw it from somewhere else, because it all goes out onto the grid and we all have access to that electricity. And these are some transmission lines. And the transmission line is simply a set of conductors, insulators, and supporting structures used to move power at high voltage, usually over long distances. So if you were at the Columbia Power Plant, you would see several sets of these leaving the Columbia Power Plant, heading in different directions to provide power to quite a bit of the state. And this is what the inside of a power line would look like. You've got the aluminum conductor. And if you know anything about aluminum, it's not the strongest metal in the world. So it actually has a strong steel core to give the cable strength. So you've got your conductor, you've got your strong steel core, and a lot of times you're going to have some type of polymer wrapping this whole thing to protect yourself from getting shocked. But the bottom line is, don't ever touch power lines. Even if you think they have that polymer, that insulator on the outside, do not touch them, because you just always want to be careful. A lot of times nowadays, we put power lines, the power companies will bury these. So in the olden days, most houses had these in the air going to their houses, but what they do now is they bury these. So a couple of words of caution. One, if you ever decide to dig in your yard, you should always call Digger's Hotline. You can look up that number, and they'll actually come out and mark the ground. They'll put like paint markings. They'll say, oh, here's where the line is. Do not dig here. Or if you're going to dig here, you got to dig there by hand to be very careful. And one of the nice things about a lot of power lines being buried these days, and you see some different size examples, is when I was a kid, we lost power a lot. We lived out in the country. And it seems like whenever we had an ice storm, something happened. A branch knocked the power lines over. So by starting to, here in Wisconsin, by starting to bury a lot of these power cables, we actually have a lot less disruptions with our power. Here is a map of Wisconsin. You can see the major transmission lines. And here is where you're going to have the Columbia Power Station. It's actually going to send power towards Madison. One transmission line is going to send it towards Fond du Lac, and the other one kind of follows its path, but then it'll go south. Now, most houses, in fact, all houses, actually have a device similar to this hooked up, and this is called a meter. It's simply a device for measuring levels and volumes of gas and electricity use. Typically, we have a gas meter and we have an electric meter. So even if you've never seen one of these, you probably have one of these. Now, this is actually starting to get old. A lot of these nowadays are newer. They're, what do I want to say, digital. So they may not necessarily have this spinning right here. They might actually have a little screen here, and then you'll just see something going across the screen. And one of the reasons why I'm pointing that out is if you still have one of the old-fashioned ones, usually along here somewhere there's a black part of the disc. And what's neat to do is just go outside and watch that. If this is spinning really fast, that means your house is using a lot of electricity. If it's spinning very slow, it means you're not using a lot of electricity. So a lot of times I would just go outside and see what's happening. Is it spinning really fast? And if it was, I would go into the house and see what's running. Things like the oven, things like the dryer, things like the furnace, they're going to cause these to spin really fast. But if none of those are running and this is still spinning pretty fast, I'm going to investigate and see what's using electricity. Now you can also get electric meters, little portable ones that you can plug your own devices in nowadays to actually see how much electricity everything produces. But back before those were invented, this was one of the ways that people would look to see how much electricity something uses, and it'd be a good way to cut back on the amount of electricity that you're using. Now, a motor, you might say, well, golly, doesn't this look a lot like a generator? Basically, it is. A motor is basically a generator that works in reverse. Now, what did a generator do? A generator took, say, wind. It took that spinning motion to create electricity. But what happens if we actually want to, say, operate a drill or use a blender? We go in the opposite direction. Now we're going to use the electricity to create this spinning motion to maybe create a fan, to spin a fan, or to run a drill, or to run the blender. So a motor is basically a generator operating in reverse. And this is just a little demonstration. You can do this at home. If we took a magnet and if we took some copper wires, so these are copper wires right here, just spinning around. If we took that magnet and just went back and forth, we would actually see the electrons. It'd be interesting if we could actually see them. So we don't actually see them, as my son would say, not literally, but electrons are spinning inside here. They are moving, and we can see as we have the north and we have the south side, this meter is going back and forth, back and forth. So that would prove that they are spinning. And here's a simplistic design of a motor. So this is hooked up to the battery. It's causing it to spin, and I'm actually going to demo one of these in class. You're actually going to get to see it. So let's talk just a few minutes about energy in Wisconsin before we take a break in part 2. Where do we get most of our energy in Wisconsin from? Well, this was taken in 2010, and when we look at it, we see there's residential. That's the blue. So I'll put an R here for residential. We have commercial, we have industry, and we have transportation. So when we look at Wisconsin energy consumption, where do we use most of our energy here in Wisconsin? Well, it almost divides it up into 4 equal parts. Industry does use a little bit more than half, 32.1%. Commercial, these are stores, retail shops. They use about 19.6% of our electricity. Transportation, this would be our cars, trains, planes. They use about 24.6%, and in our houses, about 23.8% of the electricity, or not necessarily electricity, all energy, because obviously a lot of transportation uses things like gasoline. So when we look at where all of our energy goes, it's a pretty even split, with industry just edging out the other ones, using more than 25%, and actually uses 32.1%. When we look at energy consumption estimates, where do we get a lot of our energy from? What individual source? Well, this is actually in trillion BTUs. BTU stands for British Thermal Units. It's a way of measuring energy. And we get a lot of our energy from coal. Natural gas is number 2. And then when we talk about total energy, not just electricity, but energy, a lot of it comes from gasoline or ethanol. And then there's a lot of different ones down here: jet fuel, LPG, biomass, nuclear. We do have some nuclear power plants here in Wisconsin. The next slide shows energy sources. It shows in a pie graph, and it is black and white. Sorry about that, but that's the most up-to-date information I could find, 2009. And you can see that, again, when it comes to energy consumption, just like the last chart that you saw, coal is number 1, followed by natural gas. And then here, your petroleum, that's going to be your gasoline, that's going to be your jet fuel. All that would come from petroleum. Energy sources, we got renewables, we got nuclear, and we also have some electricity. We actually import some electricity here into Wisconsin. So this is an interesting slide too. Where do we get electricity from? So the other ones were just where do we get energy from? Now this is electricity. So when it comes to energy, when it comes to electricity, coal is king by far. Most electricity in Wisconsin comes from coal, or it's by far the leader. Now look at nuclear. Nuclear is actually number 2 when it comes to electricity. Now when it comes to total energy, it's not number 2, natural gases. But when it comes to just electricity, nuclear is up there. And here we have some natural gas. We have hydroelectric, that's your hydropower dams. And then we have other renewables. And a lot of those renewables are going to be your wind generators. and this is in 2010, and this is energy production. Now this is important here in Wisconsin. Wisconsin's not that lucky. We don't have any coal. We really don't have any natural gas, and we really don't have any oil. So these three together are what we call fossil fuels. I'll just call it FF, fossil fuels. We don't have any of those. We do have a couple nuclear power plants. We do produce ethanol, biofuels, and we do have other renewable energy sources such as the wind farms that we have here in Wisconsin. But when it comes to the big three, the fossil fuels, we really don't have any, which means we do have to import a lot of energy into Wisconsin. We do have to import a lot of fuels here into Wisconsin to keep Wisconsin running. Now that does conclude part one, so we'll start part two up in just a few minutes. If you have any questions, as always, just ask your science teacher. Thank you.